Okay, thanks, Marcos, for the introduction. I'm Lawrence Benson. I'm a PhD student at the Hasso-Plattner Institute in Potsdam, and I'm going to present some work today that I did together with Philipp Ruhlich, Steffen Zeuch, Volker Markel, and my PhD supervisor, Tilman Rabel. And this work was published at EDBT this year. So today I'm going to talk about Disco, which is an approach for efficient distributed window aggregation. So let me start with a kind of a current state overview. So assume you have a smart home setting. So you have multiple homes, or maybe if you're in Berlin like me, you have multiple apartments, and each of them have some smart meters in them, maybe to check the temperature or something like that. So now we want to do something with this information. So what happens now is, say all the apartments in the building will send this data to maybe a small server that's located in the basement of the apartment building. This server will just take the data and forward it, and then this will all be processed in some cloud data center somewhere, like on AWS or Google or wherever. Then I perform my window aggregation on this, and then I get a result. Say I want to have the average temperature from the apartments or something, and then I get this. So we can see two problems here. The first of which is that we have a redundant raw data transfer. You can see this on the left side, which basically means the network hop just passes on the data. So we basically have to send raw data twice in this case, and the higher the tree gets, the more data we have to send. And we also have unused compute resources. So the servers here just aren't used, which is kind of a waste. So let's talk about the idea we came up with to tackle this problem. So we have the same settings, same smart homes, but now actually, instead of sending everything to the data center, we view these streams that come in as independent for now. And that means the network hops can actually process these streams independently. You can see, so the left network hop can actually do some window aggregation, and the right one can also do some window aggregation. And then after that, they send the intermediate results to the cloud data center, where you, the user, then can receive this result in the end. And this approach has two main advantages over the state-of-the-art other system, the current state. And the first of which is that we have a minimum data transfer. So instead of sending all the records twice or multiple times, we actually only send some metadata and the aggregated intermediate results. And also, we now utilize the compute resources along the path to the data center for more efficient computation. So this was like a high-level intro into what we're doing here. So let me give you a quick background. I guess for most of you, this is nothing new. So everyone's on the same page. We have tumbling windows that are just defined by window length. So when one ends, the next one starts. Then there's sliding windows, which also have a length, but also a slide. That means they have some kind of overlap. And then we have session windows, where we only define a window gap, and that means we collect data until we haven't seen data for a certain period of time, and then the session window ends. So in general, we distinguish between context-aware windows and context-free windows. The session windows are context-aware because they need some kind of context to know when the window ends. Whereas the context-free windows, I could basically, until infinity, I could compute all the window start and end times just by knowing the window slide is 10. I can just say start now, and then until infinity, I can just count every 10 seconds a new window starts. So they don't require any context with the data to be able to, for me to be able to compute the window bounds. And so why is this important? Quickly look at a concept called stream slicing. So for those of you who have attended Flink Forward in the last 2 years, or one of the 2 years, maybe have seen the talk by Jonas Traub, who was speaking about his library Scotty, which was a library for stream slicing. And if you're interested in this topic, you should definitely check that out. So yeah, the idea is now we have this raw stream, but we have overlapping windows, and we don't want to do a lot of redundant calculation because, like, say between window 1 and 2, there's an overlap. So if we do the aggregation there multiple times, say the sum, then I need to process data multiple times, and that's bad. So the idea is to group, or to split the raw stream into smaller chunks. We call them slices, and they're non-overlapping. So that means whenever a window starts, we create a slice, and whenever one ends, we end the slice or create a new one. And that means we get from the raw stream, we get this nice set of disjoint slices in which we can perform some pre-aggregation like this. So we can have the sum here. And then when a window is complete, say window 1, we can just take these pre-aggregates and to return the result. And when we do window 2 now, I already have the pre-aggregate of one of the slices, so I don't need to do another computation. Okay, so this was some of the background into window aggregation in general. So now how do we do this distributed? So let me quickly give you an introduction into the architecture that we came up with here. So if you think sensors here, these are basically the smart homes that we had a second ago. It's your smart heater or something that transmits some data. And this data is then collected in what we call a child node or leaf node. This is basically the server that we had in the apartment at the bottom, in the apartment building. And all the data that's collected from all these apartments is now already processed as it were its own stream. So so we do all the window calculation, we do the pre-aggregation, but instead of returning a final result, we simply pass on an intermediate result. So let's say we want to calculate the average, we can just calculate all the sum and count how many elements we've seen and just pass that on, because later on from this, we can create the final aggregate value. So we can do this independently on all these child nodes as if all these streams were independent. And now in a more realistic setting, we'll obviously have multiple levels of network hops. So now we've had a child node, and then we can have an arbitrary number of intermediate nodes. And all they do is they just collect intermediate results from their children, combine them, and then pass that on. And this can have a arbitrary height. And then finally, we reach the root node, which in this case will probably be located in a data center somewhere where your application is running to analyze this data. And then as we then collect all the final data, we can produce the final result and pass that on to the user. Okay, so this was like a high-level overview again. So how do we do this specifically? And here I want to discuss 3 different approaches. The first of which we call unique windows. And this is just a very basic concept. Let's say we want to have the average temperature of a specific or of each specific apartment. Then we know that each apartment ID will be in exactly one stream, because otherwise there would be multiple apartments. So what we can do in this case is we can just take a window here, so blue window number 1, and when we want to merge these windows, we simply can pass on the result, because we know there's nothing going on. So there's no other window that will contain data for this window. So this is the easiest case where we just simply pass on everything up. This gets more interesting now when we look at context-free windows. Just a reminder, these were tumbling and sliding windows and the such. And here we have fixed bounds, so we know when a window starts, we know when a window ends. And you can see here, even though we're on 2 nodes, the start and end points are identical. So we can leverage this knowledge simply by aligning the results. So we can see here, window 1, A and B come together, and we know the start and end bound, so we know they're the same window, and we can pass on the result, and the same for 2 and 3. So how's this implemented specifically? So let's say here we've received this window here. It's a tumbling window from second 2 to 3, and we received this from node number 3 with some intermediate values for certain keys. And now in this node that receives this, we have basically just a map of all the windows that are flying around, and so we can store this data. And here then we've already received some data from node number 1. I'm sorry, I'm not sure if you can see my mouse, so I'm not sure if that helped at all, my pointer. So yeah, you can see in the scene place that we've already received something from node 1. So we have some data in there, and we have some data saved for key A already. So we can just combine the existing stuff with the new stuff, and we can simply merge this. And yeah, now we then add to the scene list that we've also received data from node number 3. And we have this then for all the different window types. And now basically, let's say we have 3 nodes, then we'll wait for node number 2 to send its data. And when we've received the data from node number 2, then we know that we've received all data for this specific window, and we can simply return the results or pass them on. But for the other windows where we haven't seen node number 2, we still have to wait. But this gives us a very clear timing of when we can expect results and just pass them on. So yeah, for some of you might have noticed that this works really well, this approach here, when we have aggregation functions that can be combined in some. So let's say the sum or the average, I can compute these from intermediate. So I can just, if we want to calculate the sum, I can easily just add A and whatever was in A before, and I get a new sum. That's really easy. But what I can't do is when I have a holistic function. Just a quick reminder, these are aggregation functions that cannot be computed from individual elements. So you need to have the entire data present to calculate this. This would be something like the mode or the median value. For the rest of the talk, I'll be referring to the median usually. So in this case, we need to see all the data, we need to sort it, and then look at the middle element. So there's no way to do this from less data than all of it. But here, basically, we can leverage the fact that we have these slices. We've created slices beforehand. So instead of sending intermediate values, we just simply send a slice with the raw data in it, because that needs to be transferred to the root node in the end. And then we can just basically track which slices we've seen before and which we've sent. So we don't need to send data multiple times. We just send each slice once. That means we just send the minimum data. And then the same applies. So we can wait until we've seen all the data from all nodes, and then we can just pass it on. So yeah, the last window type, now this is where it gets a bit more complicated, is or at least theoretically a bit more complicated, is context-aware windows, because we have multiple nodes, and let's say we have node 1 here, and we see there are 2 windows here because there's a long gap in between. But actually, they're supposed to be 1 window, because we have on the second node, we have a window that overlaps with both, and for the same key. So this should actually be 1 window in the end. So somehow the merger needs to understand that these 3 windows here, 1A, B, and C, belong together before it produces an intermediate result. So yeah, and instead of sending the pre-aggregate as we just did, we basically now have a specific message for key B, let's say, and we have a time span between 4 and 8 seconds from node 3. And we've created a local window, so we just complete a local session window is finished with an aggregate in it. And in the merger node, we then just again collect all of these windows for the different keys. And let's say we've again from node 1 received some previous data. These were the two other windows, and you can see there's no overlap between them. But now the one we receive actually overlaps both. So then we can basically just see, okay, for this key, now we've created an overlap, so the new window must span the entire length, and then we know the extent of the window. And let's say that a new window comes in from another node, then we can see if it overlaps again or not. And an interesting part here is basically how we know when a window is complete. So we can always wait until, so as a session window is always defined basically by the data that comes in. We know when we receive a new value that ends a previous window, we basically know we're not going to get anything older than that if you disregard late events for now. So we can basically track this metadata. And then basically when we've received the timestamp that is later than the window we currently have. So if all nodes have passed on second 11, we know we won't receive anything anymore, so we can transfer the window. So I'm just going to quickly show you some evaluation results. So this is just a basic evaluation on the scale. We have a tumbling window, 1 second length, and we run this for 120 seconds. And we can see for the aggregation function average here that the blue line, so that's our approach, actually scales linearly with the number of nodes, whereas the centralized approach, which is basically the one I showed you in the very first slide, where everything is just transferred as raw data to the root node, that doesn't scale. Because basically in the setting, the one node can calculate approximately 1 million events per second. But if we have multiple child nodes, which we scale here, so one root node has multiple children, each of these children can actually compute 1 million nodes a second. And then only the intermediates get sent up to the root node. And that then has very little data because it receives basically now 8 intermediate results a second, which is very quick to merge. And interestingly now, for holistic aggregation functions like the median, where we actually need to see all the data, even though the absolute numbers is a lot lower than for the average, we still scale linearly, which is quite surprising, because actually what happens is the window calculation itself is quite expensive. So this is now also distributed. So on child node 1 and 2 and 3 or whatever, they all calculate their local windows, and later on we only need to merge these windows, and it's a lot less computational expensive than assigning window events to windows and creating the window bounds and that kind of stuff. So again, this works out a lot better. And the last thing I want to show you is the network cost quickly. Again, as I said, we only transfer the intermediate results at some point to metadata. No matter how high the tree gets, and no matter how many levels we have, for our Disco approach, the network or the number of bytes that are sent across the network just doesn't increase or it just marginally increases because every step there's only a bit of metadata. Whereas the centralized approach, you can just see every step. We just add the same amount of data again and again and again, which is fairly expensive. And obviously, if you scale this to many days or weeks or months with a lot of data, then there's a huge difference, especially in systems where network bandwidth is limited. And also for holistic approaches, the scale is better. So we have to send all the data. We can't avoid that. But actually, as we send data in slices now, instead of raw events, we just save a lot of metadata. So just sending single events is a lot more expensive because you have a lot of TCP overhead per message and that kind of stuff. So it's just we profit from some basic buffering. So quickly concluding, so we still have a few minutes for questions. Basically, I've presented you like an idea of how to approach distributed window aggregation by interpreting the streams as independent components and then merging them later on. I've given you some insights into how this can be done for different window types, and I've just shown you some quick evaluation that this approach actually makes sense, and I'm not just making up things as I go. And with that, thank you for listening, and I'm open for questions. Oh yeah, here's some links in case you're interested in the paper, the poster. The code is available on GitHub, and you can send me an email if you're interested.